Hello and welcome back, everybody. One of my favorite sections today, this is called Eigenvalues and Eigenvectors. This is quite the interesting word that I've started to use. So this word, eigen, so that's a German prefix, and it's a cognate, meaning shares some earlier etymological root. It's kind of an Anglo-Saxon or Old English, perhaps, cognate of the English word own, but kind of like the modern translation of this prefix would be like proper or characteristic, in the sense that it characterizes something. And so when we write something like eigenvalue, we're talking about a value, and in reality you should be thinking of this as a number, oftentimes it's a complex number. So an eigenvalue is a complex number which characterizes the behavior of a linear map. Or if you want to send yourself into matrix world, you could also just talk about it as a eigenvector of a matrix. So it's a complex number which is going to characterize a matrix. Every eigenvalue is paired with an eigenvector. And of course, an eigenvector you can think about as, instead of a value, now we are a vector. Big surprise there, which characterizes the behavior of a linear map or matrix. So what do we really mean by characterize? Well, we're not going to see this super well. This plays a primary role in a process called diagonalization, which we'll encounter in a little bit, and probably just as much of a role also going back to the overarching idea of this entire semester, Schrodinger's equation, if we're working with the time-dependent version. We're going to recall that h hat is a linear map, and hence it has eigenvalues and eigenvectors, and the solutions, which evolve over time, are described by, this is giving us a real hint, we're going to have psi, which is a function of time, is going to be an exponential. Well, it'll really be a superposition. You can never kind of avoid the whole idea of superpositions. So we'll have a superposition of k's and some index set. And we're going to have some basis set of vectors. These are the pure states. But basically you're going to have e to the I h bar, and then you'll have an eigenvalue times time. And in fact, I should recolor this as red because these are the eigenvectors. So eigenvectors and eigenvalues of h hat. So you're going to see that this actually gives you the solution, and so to find the solution you need to know eigenvectors and eigenvalues of h hat. So we'll go ahead and make that all a lot more clear later. But that gives me some motivation for why am I even describing eigenvalues and eigenvectors today. Let's define them. They get defined together. So we'll start with something called the eigenvalue eigenvector equation. We can write it two ways. We can write it as L when we're dealing with linear maps. So we'll say L on a vector, and I'm going to call the vector x instead of v, even though v is maybe more common for vector. I'll say L times a vector x is equal to lambda. This is the Greek letter lambda. Greek lowercase lambda. The equation is L times a vector equals lambda times a vector. Or in terms of matrices, M acting on a vector equals lambda multiplying a vector. So lambda is a complex number, but L is a linear map. And same over here, M is a matrix, but lambda is a complex number. And so the fact that you're basically, the point, maybe I'll say the point of this equation, the point of solving this equation, is finding a complex number which can take the place of a linear map. Right? In some sense, we're literally replacing L with lambda, or we're replacing M with lambda. The primary benefit being if Lx equals lambda x, then any function of L, okay, what does that mean? That's maybe a little abstract, but we'll see examples. So any function of the linear map acting on the vector x can be replaced with a function of lambda multiplying x. And this is no longer abstract. It basically lets us play games of functions on top of linear maps, which is a really cool thing to do. I'm going to list a couple of these examples here. The primary examples of these functions would be L inverse is, of course, a function, and you could do L inverse on x is lambda inverse on x. But we know what lambda inverse is, since lambda inverse is a number. It's 1 over lambda. Another example would be L to the 10th power on x. Nobody wants to calculate 10th powers of matrices or 10th compositions of functions. That sounds terrible. But you know what's a lot easier than that? Taking the 10th power of a number. It's just lambda. It's some complex number. You take 10 powers of it and you're done. And in fact, this one's really important, e to the TL. So you can take an exponential function and just rewrite it as e to the t lambda x, and this solves an ordinary differential equation, which I understand we haven't really gotten into these yet. But if I take a derivative of my exponential, e to the TL, well, you probably remember from calculus that the derivative of e to the t times a number, if I'm taking a derivative in time, is just going to be, so e to the t lambda, I'm taking a derivative in time, this just gives me lambda on x, but I'm replacing lambda with L. The point of an eigenvalue is to replace lambda with L, and so we end up solving differential equations of this form. This is where you can start to see the behavior where if I replace that L with h hat, I replace these with psi, and sure, I multiply, by I h bar, then you exactly start to recover solutions to the Schrodinger equation. So that's really kind of what it means to establish eigenvalues and eigenvectors, and the benefit of all of this. And so we're really going to focus on these equations, and maybe, let's focus on this equation. So this will be the primary equation of study. And I haven't really said what we're solving for, right? Every equation you try to solve for something. The only thing we know before we go into this process is m. So we're solving for both x as well as lambda, and that's why it's an eigenvalue and an eigenvector. So let's talk about finding eigenvalues and eigenvectors. So what we're trying to do is solve the equation m times a vector equals lambda times a vector for some vector x, probably in d-dimensional complex space, and number lambda in the one-dimensional complex space. How can we use the properties of M to find these? I think a lot of times, any sort of lecture you encounter on eigenvalues and eigenvectors, the first thing they do is they rearrange the equation. Rearrange. We can rearrange the equation just by subtracting lambda to the left and write it as mx minus lambda x equals 0, and that's really 0 as a vector. A vector containing all zeros on the inside, and you can even rearrange this a little farther as writing it as m minus lambda times the identity matrix. It's like factoring out x to the right, more or less. It's like factoring out x to the right. And once we write it as the following, m minus lambda times the identity is equal to 0, what we get out of this is this equation implies, well, actually it requires that, actually I'll write it like this, any sort of matrix equation where you say n times a vector equals the 0 vector requires that the determinant of n is 0. The only way you could possibly end up with all zeros is if your determinant is 0, and this follows directly from the properties of the determinant. And so since we require that the determinant is equal to 0, what we can get away with is just computing the determinant of m minus lambda times the identity matrix and find the values of lambda for which it is equal to 0. Because that's the only way we can possibly have eigenvalues. So let's do step-by-step process. These are the eigenvalues. That can't be overstressed. In step 2, since you found eigenvalues, now we know that for specific lambda established in step 1, we must have a solution. A solution to m minus lambda times the identity on x equals the 0 vector. So choose a lambda from step 1 and solve this for entries of x. This will be another system of equations, as always. You're all getting very good at solving systems of equations. The giant caveat here, so we'll put a little star here, the system of equations will not give a unique solution. The best we can do is find a relationship between the entries of the vector x. That's totally okay. Totally okay to find a relationship. In step 3, you choose as many as of yet determined, as of yet undetermined. No worries, I just mean the opposite of what I said originally. As of yet undetermined values in x to be 1 as we need. So you just set them equal to 1. It's no more complicated than that. You just choose them to be 1 as we need. The resulting vector is an eigenvector associated to the eigenvalue lambda we chose in step 2. So whichever one you chose in step 2, you now have found an eigenvector associated to the eigenvalue. You could say in 4, repeat steps 2 and 3 for all possible lambda in the complex numbers from step 1. So this step-by-step process is going to be your best friend for quite some time. I'll go ahead and put a nice big square around it. You definitely would not forget this anytime soon. It's basically going to be your lifeline for, I would say, the rest of the semester. I don't really think there's a way to get around this step-by-step process. On the plus side, it's incredibly straightforward. Like the step-by-steps they're really given to you. So we're going to spend the rest of today doing one example of these, and then in the worked examples section, we'll get through quite a few more examples. So let's go ahead and find one example of this step-by-step process. Finding the eigenvalue, eigenvector pairs. So they're always paired together because they kind of associate to one another for the matrix. And you could call it a linear map as well, either one. 2, 1, 1, 2. So let's follow our steps. So you're only ever given a matrix and everything else is up to you. So follow the steps. Compute determinant m minus lambda times the identity. Okay, so this is pretty important. We want to figure out what this object is first. M minus lambda times the identity. Well, let's recall. We know what m is. M is not too bad. 2, 1, 1, 2. Minus lambda. Lambda is not too bad. The identity is always 1, 0, 0, 1. It's always 1s along the diagonal. Well, I can pass lambda to the inside, right? If I pass lambda to the inside here, technically it hits the zeros as well, but the important part is that it hits the 1s and gives me lambdas along the diagonal. And then I can go ahead and subtract these in each component to get 2 minus lambda, 0, 0, 2 minus lambda. You can start here if you want. So this notion of m minus lambda times the identity, it's always just going to subtract lambdas from the diagonal. Always, oh, and I'm missing 1s. I did a good job writing that incorrectly. 1, 1. Always subtracts lambda from diagonals. It's not doing anything more complicated than that. So you can always start there and just subtract lambda from the diagonals, and then we need to compute the determinant of this object. Okay, so the determinant of m minus lambda times the identity is going to be the determinant of 2 minus lambda, 1, 1, and 2 minus lambda. And if I go ahead and compute that determinant, that's AD minus BC. And I'm going to have fun foiling. First, outside, inside, last to give me 4 minus 2 lambda minus 2 lambda plus lambda squared minus 1 at the end there. And then we're going to end up with, if I simplify this and write it like a polynomial, lambda squared minus 4 lambda plus 3. This is given a special name. This is called the characteristic equation. So I guess they decided to translate, eigen, if we go all the way back up, eigen, characteristic. They decided to translate that term into English, but not the rest of them. Whatever. So it's called the characteristic equation. Technically, at this stage, it's the characteristic polynomial. And it becomes the characteristic equation at the stage when I continue, find the values of lambda for which it is equal to 0. So the moment I decide to push this equal to 0, then it's called the characteristic equation. So find lambda in C for which lambda squared minus 4 lambda plus 3 equals 0. At this stage, it's called the characteristic equation. Now this is factorable, but it's going to be to our advantage to just use the quadratic formula whenever we can. So let's go ahead and recall the quadratic formula. as lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That would be in the sense where I have an a, b, and a c. So in this case, we're looking at lambda is negative b is negative 4, negative 4, plus or minus the square root of b squared, minus 4 times a is 1, c is 3, all over 2 times a, which is 2 times 1. I can simplify this to give me negative 4. So positive 4 plus or minus the square root of 16 minus 12. 16 minus 12 is 4, all divided by 2. This is 4 plus or minus 2 divided by 2. 4 plus 2 is 6 divided by 2, and 4 minus 2 is 2 divided by 2, or in other words, 3 and 1. Now for a two-dimensional matrix, you're going to expect to find two eigenvalues. They may be the same number. You know, repeated roots are a thing for quadratics, but you'll always find two of them when you use your quadratic formula. So that is step 1. These are your eigenvalues, 3 and 1 in this case. Now in step 2, we're looking, now we know for a specific lambda, established in step 1, we have to have a solution to the eigenvalue equation. So we're going to choose one of these lambdas in step 2. Choose a lambda from step 1. And let's choose lambda equals 3 and solve. So what does this mean? We're going to solve the equation m minus lambda times the identity against a vector x equals a vector 0. Let's translate that to something that actually makes sense. Remember from step 1, this is always subtracting lambda from diagonals. And in this case, we chose lambda is 3. So lambda is 3, we're subtracting 3 from the diagonals. That's going to be, my original matrix was 2, 1, 1, 2. And I'm subtracting 3 from the diagonals. Let's go ahead and replace x with some entries so that we can figure out what those entries should be. And let's go ahead and replace 0 with some entries, 0, 0, so we know what that's supposed to be. At this stage, I just need to solve for x1 or x2 as related to the other one. So there's always just a relationship that I'm going to get. I'm not going to get a specific number for both. I'm going to get a relationship. But anyway, let's actually simplify this and solve. So after I subtract 3 from my diagonals, I have negative 1, 1, 1, negative 1 against the vector x1, x2 is equal to 0, 0. And if I think about this as matrix vector multiplication, what I actually end up with on the left-hand side is the inner product of negative 1, 1 against x1, x2. That's negative x1 plus x2. And then the inner product of 1, negative 1 against x1, x2 is x1 minus x2. This needs to be equal to 0, 0. I can read horizontally across, and I find out that this is telling me negative x1 plus x2 is 0, or that x1 minus x2 is 0. And no matter which one I solve where, I end up with x1 is x2, and I end up with x1 is x2. So you'll notice I didn't gain anything specific about their values, but this is a relationship between x1 and x2. So now that I know that that's my relationship, I know that the original vector that I had, if I want to rewrite it down here as the vector x1, x2, I now know because of the relationship, I can go ahead and replace x2 with x1, or I could replace x1 with x2. In either case, I replace one of them with the other because of my relationship, and I find out that my eigenvector is x1, x1 for undetermined x1. In step 3, this is where I get to make a choice, right? So in step 3, choose as many as of yet undetermined values to be 1. So what I'll do to step 3, since I have this eigenvector, but it's undetermined, I'll say I have x1, x1 as my eigenvector associated to, recall I chose lambda was 3 here. Now I let x1, because it's undetermined, I just let it be 1 to recover since I let it be 1, my vector is just 1, 1, is the eigenvector for lambda equals 3. In step 4, I'm going to repeat for other eigenvalues. So 4, repeat 2 and 3 for other eigenvalues. And in fact, in this case, my other eigenvalue is lambda equals 1. I go back to step 1 at the bottom here. 3 and 1 were my two eigenvalues, so I'll choose lambda equals 1. So step 2, when lambda equals 1, I'm computing this, m minus lambda times the identity against x is 0. But m minus lambda times the identity is just 2 minus lambda, which is 1, 1, 1, and 2 minus lambda, which is 1, against x1, x2 is equal to 0, 0. What I end up with is the matrix 1, 1, 1, 1 against x1, x2 is equal to 0, 0. And if I perform the matrix vector multiplication, what I'm left with is x1 plus x2 and x1 plus x2 is equal to 0, 0. And that brings me to the case, if I look horizontally, x1 plus x2 is 0, or rather x1 is now negative x2. So this means that my vector, x1, x2, underneath x1 being negative x2, is going to give me negative x2, x2. And then the version of step 3 would be to choose that x2, since it's yet undetermined, is equal to 1, giving the vector negative 1, 1, the eigenvector associated to lambda equals 1. If I want to combine this all together, I can. So I'll go ahead and make one giant statement here. So I'll say my final statement is the eigenvalue eigenvector pairs associated to the matrix 2, 1, 1, 2 are, well, what are my pairs? My first pair that I found, if I scroll up, 1, 1 to lambda equals 3. So the eigenvalue, maybe I'll start with the value, is lambda equals 3 with vector 1, 1, and lambda equals 1, my second case I see up top, with vector negative 1, 1. That's a final statement you can make if you're asked to do something like this. I'm going to end with a couple quaint properties that I'd like to show you, because I have described how the derivative is a linear map on spaces, vector spaces of functions. And so we do have something like, if I say d dx of a function of x equals lambda times a function of x, is a valid eigenvalue eigenvector equation for derivatives. And the pairs are, well, lambda equals whatever it is, so it's some value c, and vector f of x equals e to the lambda x, since d dx of e to the lambda x by the chain rule is lambda e to the lambda x. So these are your eigenvalue eigenvector pairs of the derivative as a linear map. So you can definitely think about the derivative as a linear map. And this is really closely associated to our Fourier series. Some of you are having nasty flashbacks right now. Our Fourier series orthonormal basis, if you recall, e to the I n x, n went from minus infinity to infinity. We kind of had a little bit, there's a reason why I'll show that lambda being the imaginary number times an integer is a very useful lambda. very useful collection of eigenvalues of the derivative operator. We'll see that soon. So that's closely associated to that orthonormal basis. And we can actually look at if I take x times the derivative operator and call this entire term L, a linear map. If I'm looking for lambda times f of x, then my eigen has eigenvalue, eigenvector pairs. You can write out lambda is n, the natural numbers, and f of x is x to the n, since d dx and then multiplied by x of x to the nth power, the power rule gives me an n, x to the n minus 1, but this multiplication by x is going to add 1 to my exponent and bring me back to n times x to the n. And so we see here's lambda and here's L. And this will be closely, right, this is closely related or associated to our Taylor series orthonormal basis, which we saw as x to the nth power. Okay, maybe it should be divided by a square root if it's an orthonormal basis, but really x to the nth power and going from 0 to infinity. So that's kind of like a little bit of a tease as to where the Taylor series and Fourier series can be extracted in terms of looking at a derivative and the eigenvectors of a derivative, or maybe in the latter case, multiplying by x as well as a derivative. So that's kind of just a little bit of a tease, which is bringing us back to those earlier series and orthonormal basis decompositions of functions. But really, this step-by-step process is what you should be taking away from today. We'll have a little bit more practice with that in the next video. We'll see you then.